March 7th, 1945, 3:30 in the afternoon. The eastern end of the Ludendorff Bridge at Remagen, Germany. Captain Karl Friesenhahn holds a detonator wired to 2,800 kilograms of demolition charges packed into the steel skeleton of the bridge behind him. The calculation behind his orders is not improvised. It is the foundation of Germany's entire Western strategy in the spring of 1945. The Rhine cannot be bridged by an advancing army under combat conditions fast enough to matter. Drop every span into the river below, and the Americans face a 1,000-foot wide obstacle with a current that runs cold and fast enough to drown an unprepared man in minutes. German military engineers had run the numbers. A division-scale crossing, even under the most favorable conditions, would require a minimum of 48 hours just for the bridging work, longer under fire, and longer still if German artillery and air power could interdict the effort. 6 to 8 weeks, Berlin calculated, was the realistic delay a destroyed Rhine crossing would buy. 6 to 8 weeks was enough time to reorganize shattered divisions, dig new defensive lines, and search for any outcome other than unconditional surrender. Friesenhahn presses the detonator. The bridge shudders. Smoke, fire, a thunderclap that rolls down the gorge and echoes off the 600-foot basalt cliff on the eastern bank. The structure lifts slightly into the air, then it settles back down onto its own foundations, intact. The demolition charges had been placed and wired by men working under fire, with materials degraded by weeks of partial sabotage and improvised repair, against a structure that Russian prisoners of war had originally built in 1916. To standards that turned out to be inconveniently robust. Whatever the precise technical failure, and German post-war courts-martial would spend considerable energy trying to assign it, the practical result was immediate. American infantry were already running. What follows is not simply the story of one bridge surviving one explosion. It is the story of a strategic calculation that was engineering correct and catastrophically incomplete, and of a different category of engineering, conducted 18 months earlier in factories, training ponds, and after-action review rooms scattered across England, Luxembourg, and Belgium, that had already made the Rhine's status as Germany's final wall obsolete before a single American boot touched the riverbank. To understand why German planners trusted their math, you have to understand how sound the math actually was. The Rhine runs 766 miles from its source in the Swiss Alps to the North Sea, and at Remagen it is not merely wide. It is, in the words of the combat engineers who later studied it with the specific respect professionals reserve for genuinely dangerous terrain, alive. The current near Remagen could spin an unanchored small boat without warning. The main channel reached 60 feet in depth. In March, the water was cold enough to kill an unprotected man in under 30 minutes. The U.S. Army Corps of Engineers had issued an official survey only weeks before the crossings began, and its conclusion was unambiguous. At no point along the river's length was it fordable, even at low water. German Field Marshal Karl von Rundstedt had studied this terrain for months and reached the conclusion his engineers' calculations supported. The Rhine was, in his own phrase, an excellent natural obstacle, the structural backbone of Germany's last defensive position in the West. Not since Napoleon Bonaparte, more than a century earlier, had a hostile army crossed the river in force, and Napoleon had done it without facing artillery that could obliterate a pontoon span in a single registered shot. The historical precedent reinforced the engineering conclusion at every level of the German command structure. This river had held against everything thrown at it for generations. In the specific technical conditions of 1945, heavier equipment, faster current data, denser German artillery coverage along the eastern bank only strengthened the case. The arithmetic behind von Rundstedt's conclusion accounted for bridging equipment weight, current speed, anchor depth requirements, and the time needed to lay pontoons in a river actively trying to carry them downstream. None of it was wrong as engineering. It was simply built entirely on the assumption that the Americans would need to construct a bridge from nothing, using equipment and procedures that matched what German intelligence had on file from earlier in the war. On March 1, 1945, demolition teams were deployed to all 21 major Rhine crossings under direct authorization from Hitler. Destroy every bridge the moment Allied forces came within range. Do not allow a single crossing to survive intact. Force the Allies into the river-building problem. German calculations said they could not solve quickly enough to matter. 18 of the 21 were successfully dropped. Cologne fell. Dusseldorf dropped on schedule. Koblenz went down before a single Allied soldier got close enough to see it happen. German demolition crews were, on the whole, competent, well-drilled, and entirely convinced they were buying their nation the 6 to 8 weeks its general staff said it needed to reorganize. The German calculation had one blind spot, and it was not a calculation at all. It was an assumption so basic that nobody in the planning apparatus thought to interrogate it. The Americans would need to build a bridge. Nobody seriously modeled what would happen if the Americans simply took one. Second Lieutenant Karl Timberman was 22 years old, born in Frankfurt to a German mother and an American father, a veteran of the First World War occupation force who had fallen in love, deserted the U.S. Army to stay with her, and eventually brought the family back to the United States, settling in West Point, Nebraska. Timberman grew up the son of a former deserter in a small Great Plains town, carrying an American allegiance and a German surname through a war that made both facts conspicuous in ways his neighbors rarely let him forget. He had enlisted in 1940, fought across France and Belgium, been wounded during the Battle of the Bulge, and returned to his unit on March 6, 1945, one day before he was given command of Company A, 27th Armored Infantry Battalion, replacing a commander who had been hit the previous day. He had held that command for roughly 17 hours when his lead platoon pushed through the trees on the ridge above Remagen on the afternoon of March 7th and stopped. The Ludendorff Bridge was still standing. German traffic, vehicles, fleeing soldiers, civilians, livestock, was still crossing it. Timberman radioed the discovery up the chain. The previous night, General William Hogue had told the task force commander something close to a direct order disguised as encouragement. If you can seize that bridge, your name goes into the history books. Nobody had seriously expected the opportunity to materialize. Every operational plan, German and American alike, assumed the bridge would be rubble by the time any American unit reached visual range of it. It was standing in the March light regardless, and Timberman had perhaps 30 minutes to decide what his company would do with it before German engineers, who had already begun their demolition sequence, found a way to finish the job. What he decided was to go. His company crossed under direct fire, while German engineers, having already failed once, scrambled to find a second method of destroying the span. A scramble that, as the courts-martial weeks later would establish, produced exactly the kind of rushed, improvised failure that compounds the first one. Sergeant Alexander Drabick, a tall, lanky former butcher from Holland, Ohio, ran down the center of the bridge, zigzagging fast enough that he lost his helmet, becoming the first American soldier and the first invading soldier of any nationality since Napoleon to set foot on the eastern bank of the Rhine. His squad followed, and all of them made it across, weaving between gaps in the decking where earlier, smaller charges had already done partial damage. Timberman reached the far bank shortly after and began clearing the Erpeler Ley Tunnel, a 380-meter passage blasted through solid basalt where hundreds of German soldiers and civilians had taken shelter, without knowing its length or how many people were inside it. He simply moved forward into the dark with his men, weapon ready, treating the unknown interior as another tactical problem rather than a reason to wait for reinforcement or daylight. Asked in those first minutes what his men should do if the bridge finally collapsed while they were still on it, his answer was immediate: swim. The bridge held for 10 more days. What made those 10 days strategically decisive was not the bridge itself. It was what was already waiting, fully built and staged, on the western side of the river. A body of preparation that German intelligence had never adequately assessed because it had never taken the underlying engineering culture seriously enough to study it. In 1940, Donald Bailey, a civilian engineer with the British War Office, was riding back from a failed bridge test near Christchurch, England. British military engineering was, by his own post-war account, in a state of quiet panic. German armor was getting heavier every year, and no portable bridge design in the British inventory could carry it. The existing designs dated to the First World War, with weight limits the new generation of tanks simply exceeded, meaning that even where bridges existed, they were becoming liabilities rather than assets, structures that would collapse under exactly the vehicles an advancing or retreating army most needed to move across them. Bailey pulled an envelope from his pocket and sketched, on the back of it, a system that working military engineers initially doubted on sight. A modular bridge built from identical steel panels weighing 570 pounds each, light enough for 6 men to carry, connected with simple steel pins rather than welds. No cranes. No foundations. No specialized engineering degree required to assemble it correctly. Panels, pins, and men with hammers. Stack panels 2, 3, or 4 layers deep for greater load capacity. Mount the assembly on pontoons for water crossings. The design scaled almost without limit, and it could carry 40-ton tanks across spans that conventional fixed bridge engineering would have required months and permanent foundations to achieve. The design went from envelope sketch to military service in roughly a year. By 1942, it was deployed in North Africa. By mid-1944, the United States had licensed it and was manufacturing Bailey bridge panels at a rate of 20,000 per month across more than 650 factories, an industrial mobilization scale that had no parallel on the German side for any single piece of combat engineering equipment, let alone one initially sketched by a civilian on an envelope in the back of a car. Total wartime output, roughly 700,000 panels, the equivalent of more than 200 miles of deployable bridge, stockpiled and staged before a single span touched the Rhine. Dwight Eisenhower, asked after the war to name the 3 most decisive pieces of Allied technology in the European campaign, named radar, the heavy bomber, and the Bailey Bridge. Not the Sherman, not the Garand, not any weapon at all. The selection was deliberate and specific. Of every piece of equipment that crossed into Germany with the advancing Allied armies, Eisenhower considered the modular bridge more decisive to the campaign's outcome than anything designed to kill. German planning had assessed Allied bridging capacity using the equipment inventory current as of roughly 1941. The Bailey Bridge had been classified tightly enough that even Allied newspapers had no public knowledge of it until after D-Day. It does not appear at the level of operational detail that would have mattered in surviving German intelligence assessments of the Rhine defense, a gap that German military intelligence, by most post-war accounts, never fully closed even after encountering Bailey spans repeatedly in Italy and France. The bridge itself, however remarkable, was only the hardware. The harder problem, the one that determined whether hardware translated into a usable crossing under direct fire, had been worked out through a much less glamorous process: failure, documented and converted into doctrine. German military intelligence's broader failure to track American engineering capability was not an isolated oversight specific to the Bailey Bridge. It reflected a consistent pattern across the war. German assessments of Allied capability tended to weight combat arms, armor, infantry quality, artillery doctrine, far more heavily than logistics and engineering, categories that German military culture had traditionally treated as supporting functions rather than independent sources of strategic advantage. This was not stupidity. It was a coherent worldview, consistent with a military tradition that prized tactical brilliance in operational maneuver as the decisive factors in war, and that had, for most of its history, been broadly correct to do so. The Wehrmacht of 1940 had won campaigns through exactly that combination of qualities. Fremde Heere West, the German intelligence branch responsible for assessing Western Allied forces, maintained detailed dossiers on Allied armor divisions down to individual tank models and crew training standards. Its files on Allied engineer battalions, by contrast, were thin enough that post-war Allied historians reviewing the captured archive found almost no operational detail on bridging unit capacity, production rates, or rehearsal schedules. The branch had simply never built the collection apparatus to track a category of unit it did not consider worth tracking. River crossings under fire are among the most operationally catastrophic tasks an army can be ordered to perform. The work is slow. It offers no cover. Every piece of bridging equipment is a pre-registered artillery target the moment the enemy identifies the crossing site, and the men doing the physical labor stand exposed in moving water with no ability to return fire while shells search for them. American combat engineers had learned this lesson the expensive way well before they reached the Rhine. The Moselle River crossing in September 1944 had been costly. General Patton's Third Army lost men, equipment, and several days of advance to a river crossing that German defenders had anticipated and prepared for with more care than American planners had initially credited them with. The crossings of the Ruhr and the Saar produced their own specific catastrophes in the months that followed. Boats capsizing in current that engineering surveys had underestimated. Pontoons destroyed before anchoring was complete because German artillery observers had better visibility of the crossing sites than American reconnaissance had assumed. Entire bridge sections torn loose and swept downstream when anchor points failed under load conditions the original calculations had not modeled correctly. Each disaster generated an after-action report, filed through a chain of command that treated these documents as operationally binding rather than as bureaucratic formality. Each report was analyzed for the specific mechanical or procedural failure that had caused it, not in general terms, but down to which anchor design had failed, at what current speed, under what loading, and what alternative method had been tried successfully elsewhere. Each identified failure became a new training requirement, distributed to engineer units across the theater, regardless of whether they had personally experienced the failure being corrected. By March 1945, American engineer units had rehearsed Rhine-scale river crossings on the Meuse River in Belgium, under artificial moonlight and simulated combat conditions, repeatedly, timing every phase of the operation and identifying which men performed which tasks fastest under realistic stress rather than relaxed training conditions. They had calculated exactly how much current a given pontoon design could tolerate before drifting past its anchor point, expressed not as a general guideline, but as specific current speed thresholds tied to specific anchor weights and cable lengths. They had studied German defensive positions along the Rhine from aerial photography and worked out probable artillery trajectories against likely crossing sites in advance, pre-identifying which stretches of riverbank offered German gunners the clearest fields of fire and planning construction sequences that minimized exposure during the riskiest phases of assembly. Steel mills in Luxembourg had been producing custom-cut treadway beams for months, run on production schedules tied directly to projected Rhine crossing dates rather than general wartime demand. American shipyards had mass-produced lightweight river assault craft specifically sized for the width and current characteristics the Rhine survey data predicted. Seagoing landing craft capable of ferrying tanks across the Rhine had been shipped from England through Antwerp, loaded onto oversized trailers, and physically driven on German roads by truck to forward depots near the river. Some of those loads were wide enough that convoy routes required demolishing the corners of houses in small villages to get through, an operational cost that planners had accepted months in advance as the price of having the equipment exactly where it would be needed exactly when it would be needed. By the staff estimates compiled after the campaign, the forward depots supporting the 1st Army sector alone held enough pre-staged treadway and Bailey components to open roughly 4 simultaneous crossings without resupply from the rear, a margin that had nothing to do with the specific bridge German engineers had blown at Remagen and everything to do with a stockpile built to outlast any single point of failure. March 8, 1945. The Ludendorff Bridge was still standing, but barely. German engineers had managed enough secondary damage that American inspectors gave it an uncertain prognosis. Functional for an unknown number of additional hours, under increasing artillery fire from multiple directions and the beginning of attack runs by the Arado AR-234, the world's first operational jet bomber. If the structure failed before an alternative crossing existed, roughly 25,000 American soldiers already on the East Bank would be stranded, cut off from resupply, reinforcement, and any path of withdrawal if the German counterattack the bridgehead was already drawing proved stronger than First Army's ability to hold the perimeter. Lieutenant Colonel David Pergrin, 27 years old, a Penn State civil engineering graduate commissioned through ROTC, had spent the preceding 9 months commanding the 291st Engineer Combat Battalion through some of the war's harshest fighting, including the Battle of the Bulge, where his men, armed with little beyond demolition charges and rifles, had stood directly in the path of SS panzer columns and blown bridges under fire to slow the German advance at a moment when regular infantry units were retreating around them. The battalion's reputation by March 1945 was built on exactly this kind of improvised competence under conditions doctrine had not anticipated. His new order? Build a 1,100-foot pontoon bridge across the Rhine, the longest tactical span ever attempted under enemy fire in under 36 hours. Standard Army doctrine for treadway bridge construction specified roughly 50 feet of progress per hour under daylight, non-combat conditions, meaning a structure of this length should require approximately 22 hours under ideal circumstances. The actual circumstances were close to the opposite of ideal. German artillery had the bridging site under direct observation from high ground on the eastern bank, adjusted continuously as American spotters worked to identify and suppress each gun position in turn. German armor near the village of Erpel was delivering direct fire onto the engineers and their equipment from ranges close enough that individual muzzle flashes were visible to the men working in the water. The Luftwaffe was running strafing passes between artillery barrages. Floating mines drifted down on the current, released upstream specifically to find the pontoons and detonate against their hulls. The air temperature hovered just above freezing, cold enough that men working in the water for extended shifts risked hypothermia on top of the combat exposure. Construction began the morning of March 9th. Engineers worked in 2-hour rotations, not from fatigue, but because remaining in any fixed position longer than that made a man a reliably targetable object for German artillery observers who had learned to register fire on positions that held still. Pontoons were floated into position, anchored against the current, connected, and decked. When a shell destroyed a completed section, the wreckage was cleared and the section rebuilt from the same point by the same crews without a change in plan or a request for different methods. Men worked through the night under lighting that made them visible targets because stopping was the one option that was not available. Every hour the structure was not yet complete was an hour the 25,000 men on the East Bank remained dependent on a single damaged, failing bridge. At 5:10 in the afternoon on March 10th, 35 hours and 10 minutes after the first pontoon entered the water, the structure touched the eastern bank, 1,100 feet. The first Allied bridge across the Rhine, and the longest tactical span of its kind ever assembled under direct enemy fire to that point in the history of military engineering. When the original Ludendorff Bridge finally collapsed on March 17th, killing 28 American combat engineers who had spent 10 continuous days shoring up and repairing a structure that German artillery, German aircraft, and a dedicated German demolition effort had all failed to bring down on schedule, Pergrin's pontoon bridge had already been carrying a division's worth of men, vehicles, and equipment across the river for a week. 2 weeks later, and roughly 20 miles north, at Wesel, a different American engineer unit confronted the same calculation from a different angle, in support of Montgomery's much larger and more conventionally planned Operation Plunder, an assault preceded by 5,000 guns and a massive airborne drop, the kind of methodical, heavily resourced crossing that German doctrine would have recognized as the expected form of Allied river assault. A general inspecting the proposed site put the timeline at 48 hours. A colonel reviewing the same maps and the same available resources estimated 36. A lieutenant colonel who walked the riverbank personally thought perhaps 24 was achievable. The enlisted engineers of the 17th Armored Engineer Battalion's Companies E and C, who were not consulted on any of these estimates and likely would not have cared much about them if they had been, began work at 8:35 in the morning on March 24th. Their assignment? 1,146 feet of M2 treadway bridge, longer than the world record for this specific bridge type, which had been set under ideal peacetime conditions at 250 feet in 3 hours. Their task required laying more than 4.5 times that distance, under sustained artillery fire, in river current, with German machine gun positions actively engaging the worksite from concealed positions on the eastern bank that artillery preparation had not located. By 4 in the afternoon, the first truck crossed. 9 hours. 25 trucks had ferried the bridge's components. 93 pneumatic floats, more than 1,000 feet of treadway decking, from the forward depot to the construction site, and a unit of soldiers had connected, anchored, and decked the entire span while under fire that never fully stopped. Lieutenant William Doyle of Kansas City, the junior officer who directed the work, was asked afterward how his men had managed it. His answer, recorded without embellishment, "I guess we just were scared and wanted to get out of there in a hurry." The Army's own treadway construction manual, revised after the war specifically to reflect what Wesel and Remagen had demonstrated, raised the doctrinal expected rate by a factor of roughly 3, a tacit admission that the pre-1945 50 feet per hour standard had been calibrated to crews who had never been pushed to find their actual ceiling under combat pressure. Downstream from Wesel near the Dutch border, the Royal Canadian Engineers of the 2nd Canadian Corps built a floating Bailey Bridge they named Blackfriars, after the bridge across London's Thames. 1,814 feet from ramp to ramp, the longest Bailey Bridge ever constructed, completed in 2 days and rated for 40-ton tank traffic. By March 24th, 9 days after Pergrin's pontoon bridge had opened at Remagen, American and Allied engineers had completed 12 separate combat-capable crossings of the Rhine. While Montgomery's set-piece operation drew most of the contemporary press attention, George Patton had crossed the river entirely on his own terms 2 nights earlier. On the night of March 22nd, with no preparatory artillery, no airborne component, and no advance announcement to anyone outside his immediate staff, Patton sent the 5th Infantry Division across at Oppenheim in rubber assault boats, in near total silence, using a handful of engineers who had quietly prepared the crossing in advance. By morning, the division held the east bank. Knight telephoned General Omar Bradley to report the crossing, then instructed him to release the news to the press immediately, specifically so the announcement would precede Montgomery's far larger, far more publicized operation by a full day. The line attributed to Patton afterward captures the tone exactly. He wanted the world to know Third Army had crossed before Montgomery started. A sign American engineers posted at the Remagen site after the bridgehead was secured read, "Cross the Rhine with dry feet, courtesy of the 9th Armored Division." It was the kind of joke an army makes only after it has solved the problem so thoroughly that the problem has become a punchline rather than a threat. Hitler's response to the loss of the bridge was not strategic. It was immediate and punitive. He relieved Field Marshal Walter Model of command, replacing him with Albert Kesselring, and ordered courts-martial for the officers held responsible for the demolition's failure. 4 men, Major Hans Scheller, Major Herbert Strobel, Captain Willy Brodtke, and Captain August Kraft, were convicted of dereliction of duty and executed by firing squad within days of the proceedings, a speed that itself signals how badly Berlin needed someone, anyone, to bear formal responsibility for an outcome the engagement math had said was effectively impossible. Brodtke, notably, was tried and sentenced in absentia. He had already been captured by American forces at the bridge itself and was sitting in a POW camp while a German military court sentenced him to death for failing to destroy the structure he no longer had any ability to influence. Friesenhahn, the engineer who had actually pressed the detonator, was cleared. The investigation concluded the charges had failed due to defective materials and faulty placement that predated his involvement, not through any failure of nerve or duty on his own part. The distinction mattered enormously to the men judging the case and meant nothing to the strategic situation it was meant to address. Kesselring himself called it the crime of Remagen. Goering stated the capture made a prolonged defense impossible. Wagner, Model's chief of staff, later wrote that the affair should be considered grounds for ending the war outright. None of these men were prone to dramatic overstatement in their official correspondence. The language itself is the data point. Germany's response over the following 10 days was correspondingly disproportionate. a catalog of escalating desperation that reads, in retrospect, like an inventory of every weapon in the German arsenal capable of being pointed at a single fixed geographic point. Infantry assaults on the bridgehead, artillery from multiple directions, repositioned repeatedly as American counter-battery fire located and suppressed each new firing position. Floating mines released upstream specifically to drift into the pontoons under cover of darkness. A specialized naval demolition team, 7 SS combat swimmers equipped with Italian-designed underwater breathing apparatus, entered the river 17 kilometers upstream and floated down in darkness using oil drums for buoyancy, intending to attach charges directly to the structure. American searchlights, mounted specifically to cover the bridge approaches at night, spotted them, and all 7 were captured before reaching the target. The Arado AR-234 jet bomber flew 11 attack missions against the bridge and scored no hits, undone partly by the density of anti-aircraft fire the Americans had concentrated around the site, and partly by the inherent difficulty of hitting a narrow linear target from a fast jet aircraft with 1945-era bomb sights. Germany fired its 600mm Karl super heavy mortar, one of the most powerful artillery pieces ever built, a weapon originally designed to crack fortress walls and bunker complexes 14 times at Remagen without a significant hit, the shell's enormous individual destructive power rendered largely irrelevant by the difficulty of achieving the precision a narrow bridge target required. 11 V-2 ballistic missiles, a weapon designed for city-scale terror bombardment against London rather than precision point targets on a battlefield, were aimed at the bridgehead, the first and only time in the war the V-2 was used against a tactical military target rather than a civilian population center. All 11 missed, their guidance systems simply incapable of the accuracy a structure a few dozen feet wide demanded. American anti-aircraft units defending the site eventually constituted, by post-war count, the densest concentration of air defense assembled at any single location in American military history to that date. None of it changed the underlying arithmetic. In the 18 days between the bridge's capture and the American breakout from the bridgehead on March 25th, more than 125,000 American soldiers crossed the Rhine at Remagen, 6 full divisions, with their tanks, their artillery, and the trucks that kept all of it supplied. The German command had thrown infantry, naval commandos, the world's first jet bomber, its heaviest siege artillery, and ballistic missiles designed for strategic terror bombing at a single river crossing. And every one of those efforts had failed to interrupt a logistics flow that depended, in the end, on bridges built by enlisted engineers working in 2-hour shifts in freezing water. The forensic accounting is this. Germany's calculation about the Rhine was correct, as engineering and incomplete as strategy. The river was exactly as formidable as German planners believed. No army could ford it. No conventional bridge could be improvised across it quickly enough to matter under the equipment standards German intelligence had on file. What the calculation never priced in was a capture rather than a construction, and behind that single contingency, an industrial and training apparatus that had spent 18 months converting every prior river crossing failure into a documented procedure, every promising sketch into a production line, and every doctrinal time estimate into a number that trained crews under fire would simply beat. The Bailey Bridge existed because a civilian engineer sketched a solution to a problem the British military establishment had already half accepted as unsolvable, and because an American industrial base then took that sketch and turned it into 700,000 manufactured panels before a single one was strictly necessary. The 291st 35-hour pontoon span existed because David Pergrin's battalion had already survived the bulge doing improvised engineering work under direct tank fire and had internalized exactly what that kind of pressure required. Not panic, not heroics for their own sake, but the specific operational discipline of continuing a methodical process while people were actively trying to kill the men performing it. The 9-hour Wesel Bridge existed because the 17th Armored Engineers had rehearsed the procedure on the Meuse until execution speed stopped being a variable anyone needed to think about consciously, until the sequence of float, anchor, connect, deck had become something closer to a single continuous motion than a series of discrete decisions. None of these men were exceptional in the way German doctrine prized individual battlefield brilliance. The inspired commander, the technically gifted specialist whose personal genius compensated for institutional limitation. They were the product of a system that had spent 2 years turning specific documented failures into specific rehearsed solutions, then placing trained crews and pre-staged equipment at the exact point where the next failure was expected to occur, so that when the moment actually arrived, the response required no improvisation at all, only the execution of a sequence that had already been practiced under conditions designed to simulate the worst case rather than the best one. The numbers from the broader Rhine campaign confirm what the individual bridges demonstrate in miniature. 12 separate combat-capable crossings were completed within roughly 3 weeks of Remagen's capture. Montgomery's heavily prepared crossing at Wesel was supported by a treadway span completed in 6 hours and 15 minutes. A second, even faster confirmation that the 17th Armored Engineers' 9-hour effort downstream had not been a singular fluke, but a reproducible standard. The First Army's bridgehead at Remagen expanded to roughly 40 kilometers wide and 15 kilometers deep within the same period. By the end of March 1945, an estimated 650,000 Allied soldiers had crossed the Rhine. Germany's projected 6 to 8 week delay had collapsed to roughly 72 hours of genuine strategic uncertainty before the outcome became, in the judgment of Germany's own senior officers, essentially settled. Karl Timberman, the 22-year-old who had commanded his company for 17 hours before running it across a bridge the German High Command had ordered destroyed, was discharged in December 1945, re-enlisted, served in Korea, and died of a malignant tumor at Fitzsimon's Army Hospital in Denver on October 21, 1951. He was 28. He is buried at Fort Logan National Cemetery in Colorado, the same post where his father's military record had begun, troubled, in 1919, a closing symmetry that Timberman himself never lived to comment on. Alexander Drabik, the butcher from Holland, Ohio, who had been the first invading soldier to set foot on the Rhine's eastern bank since Napoleon, lived until 1993, dying in a traffic accident on the way to a reunion of his old unit, an ordinary death decades removed from the bridge that received barely a mention in the regional press where it occurred. David Pergrin lived to write his own account of the crossing, First Across the Rhine, a book built less around personal heroics than around the specific operational lessons his battalion had learned and applied, the kind of record that exists precisely because the system he served valued documented process over individual legend. Donald Bailey, knighted in 1946, died in 1985. Modified versions of his envelope sketch are still deployed today in disaster relief operations and military engineering exercises around the world, 60 years after a failed bridge test sent him looking for a better answer on the drive home. 28 American combat engineers died holding the original bridge together for 10 days that the men repairing it knew almost from the start might not be enough, and were largely right, and built the next bridge anyway, completing it in 35 hours before the first one finished failing under them. Germany had the engineering mathematics correct. It had calculated against the wrong engineers.